Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we had earlier written these energy conservation laws and we had then compared it to this very simplified circuit of an induction motor, where this entire induction motor is replaced just by a simple inductance and a resistance. And the idea was to show that with this very simple representation of an induction motor, you can begin to see certain analogies between the power equation and the energy equation. Also, again, it's important to remember these are two different equations. One is an energy equation, one is a power equation. So therefore, we cannot equate them directly, but we are beginning to see certain analogies. So in this lecture, I'll continue with this analysis and I'll talk about how we can expand it a little further. So as always, before I start the lecture, a little bit of brief background. That if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So pythonpowerelectronics.com is the homepage of this project, which is Python Power Electronics, and the objective is, you can see, is to provide education and tools in the field of open source tools in the field of power electronics. So if you go to the home page, you will see these are the 4 buttons which you will see right in the beginning. And if you click on this button Learn, it will take you to the list of courses. So as of now, I have 5 courses which are online. The very first course is Simulating Power Electronic Circuits Using Python. And in this I talk about the basics of how you can use Python and Python Power Electronics to simulate simple power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python Control package to analyze and design controllers for power engineering applications using the example of a single phase inverter connected to a single phase grid. The very last course I have is a free course called Why Specialize in Power Electronics, and this is a course which is targeted towards either junior undergraduate students or even high school students who have not yet chosen that domain of specialization, and this is to show some of the challenges and opportunities available in power electronics so that they may choose it as a domain of specialization. So this is a free course as compared to the others. All these courses are hosted on 2 platforms, which is Decibels Labs and Udemy. If you click on any of these buttons, it will take you to the link for the course. The link for this page is available in the description of this video, so if you're interested, please do check out the description of this video. So with this, let me get back to my lecture. So as I said, we are already making some kind of an analogy. So if you look at this entire equation where electrical energy, we know input electrical energy has to be equal to the output mechanical energy plus the energy stored in the magnetic field. Why? Because a magnetic field is fundamental to the operation of any machine, right? Any machine operates on the basis of a magnetic field produced within it. So therefore, there will be energy stored in the magnetic field. Besides that, there are electrical losses, there will be mechanical losses such as friction losses, vibration losses, and there will be magnetic losses such as hysteresis losses and eddy current losses. Okay? And this is what it all is. Now, we had seen with this simple expression, or rather this very simple representation of the motor, where I had thrown away all those details, right? Like for example, if you look at the equivalent circuit, we had a fairly detailed equivalent circuit. Now we are taking all these details away and just saying that if we represent an induction motor by a simple inductance and a resistance, nothing more than that, right? Then in that case, we can come up with this particular equation. So we can say that the power, input power to this motor, which is equal to V into I, is equal to the current I multiplied by the differential with respect to time of the product L into I, and plus the ohmic losses, which is I square R. right? So I squared R is very clear. We know it's ohmic losses. It is this quantity, that is the product of the current I multiplied by the differential with respect to time of this product L into I. Now the reason why this L is inside the differential is because we are saying that it need not be a constant. And the reason why it's not a constant is because we know that in induction motor, there are several different types of inductance. There is self-inductance, there is mutual inductance, and therefore, if we were to represent the entire induction motor as a single inductor, then in that case, this inductor would not be constant, right? As we've already seen in the previous in several of the previous lectures, of all these, right, of all these different inductances which are there, some will be independent of the rotor angle and therefore constants, while others are dependent on the rotor angle, right? Now this we had gone through before. If you are not sure, just go back to some of the previous lectures. But otherwise, what's important to understand is if we represent the entire induction motor as a simple inductor, then this inductor is not a constant. And therefore, you cannot say that this differential of the inductance with respect to time is zero, right? So now this little unknown quantity here is what is intriguing, because we know the ohmic losses. We don't know what this is, and we know the power. So the power is equal to the ohmic losses plus some unknown quantity. And now we are beginning to make this analogy. We say that this unknown quantity is in some way related to this summation, that is mechanical energy plus energy stored in the magnetic field. So now the question is, what if we try to expand it? So let's say, for example, let's come over here and let me write this equation again, that is I into D. Actually, it will always change, so let me go back and change it. L into I divided by dt. And for that instance, we can just go back here and change it, this autocorrect. I can't believe it. Okay, that's better. So now we have this expression here. If we want to expand it, what would it be? Quite simply speaking, if we say that this inductance is not a constant, but is instead a variable, then we can use this simple differential law by expanding it out. So therefore, we can say I into di by dt, that is, we are taking this constant I, and we say I into I, so I into I into dl divided by dt. Now I need to go fix the i's, bothersome, but what to do? Okay. So now, oh, come on. Okay, so we have simply expanded this differential by saying that in one case we are considering L to be constant, differentiating I with respect to time, and in the other case we are considering I to be constant and differentiating L with respect to time. This is a very simple differential law, right? All we are saying is if we take a product AB and we differentiate it with respect to time, and we say that A is some function of time and B is another function of time, right? That is, A is a function of time f of t, B is another function of time g of t, then in that case, this product can simply be expanded to A dB by dt plus B dA by dt. This is a simple differential law, nothing more. This is something we learned in high school, so nothing to do with power electronics or electrical engineering or control or anything of that sort, right? So this is all I'm doing. Now, if you look at this equation, we see that here we can simplify this to some extent. So let me just put I squared into dl by dt. Okay, and we can maybe even remove this multi asterisk for that reason. Now, let's say we have this. The question now arises, what about this equation, right? We are saying that this equation here is equal to, here, if we can replace it here, that is input power is equal to something plus losses, ohmic losses. Now, the question we are now saying is, we have now equated these two. We have equated these two. So we are saying that we didn't equate it, but we are trying to draw an analogy. So let us now go one step further and say that this expression is equal to mechanical power plus rate of change of energy stored in the magnetic field, right? And of course, we can say these losses for now, we can just forget these losses for now. So we can say that how we're going to equate all these electrical losses, mechanical losses, magnetic losses, and how we are going to represent all these losses by this simple resistance is for now not necessary. So for example, as I already said, unless you're looking at a very detailed model of an induction motor where we have very specific expressions for the eddy current losses and the hysteresis losses and the mechanical losses, it is quite possible that we can represent a resistor that brings in all these losses together, right? So for now, we are saying that this expression here is the sum of mechanical power and the rate of change of energy stored in the magnetic field, right? And here you see this is exactly the same thing we are getting at. We don't have an expression, we don't have an equation for this yet. This is just an expression. Now here we have gone one step further and said that this expression has an equation, right? Now you might say, where is this going? Is it any use? Well, the question then is, let's try to find out. So now if I were to go and say that if I were to say, for example, that if we take this expression here, this same equation, this same circuit rather, that is, you have an inductance and a resistance, and that is supplied by an AC voltage. Now we are saying that this is a simplified circuit of an induction motor. Now let us suppose we forget for an instant that this is an induction motor, right? Just forget that this is an induction motor and therefore this is something which can move. If this is not something which can move, the question then arises, what happens to the input power which is fed? So let's go back and write this equation. Again, here we are assuming the circuit feeds a simple inductor, right? So forget about the moving part of an induction motor. We are merely saying, actually maybe I should write this here because we are doing a comparison. So let me put this here. Assuming that the circuit feeds a simple inductor. Now, if it were to feed a simple inductor, then in that case we can write this equation. V is equal to D of, it's important to understand this is the induced EMF plus I into R, right? This is the induced EMF. Now, if I were to go ahead and say, oh my god, autocorrect, okay, V is equal to E plus IR. Again, we are coming back to the same question as to what to do with this IR. Right away, let me just get rid of this and say V is approximately equal to the induced EMF, right? This is approximately. Here, we are neglecting resistive drop. Okay, just let's get rid of that completely because we are anyway saying that we don't want to go into this loss estimation and how to break up the losses and things like that. So let's just get rid of it right away. So if V is approximately equal to the induced EMF, then V is approximately equal to L di by dt, right? L di by dt. Now you might be tempted to just write this, right? Because it's an inductor, right? It is an inductor and therefore we are saying that we don't really care about the rotational aspect. Because here we said that because this circuit represents an induction motor, the inductor cannot be constant. Here, of course, if we say that we assume this circuit to be an inductor, then this inductance has to be a constant. Now, what if I say, let's keep assuming that this circuit is an inductor, but let us go back to our initial assumption that this inductance is variable. Alright, so what we're trying to do is we are trying to relax our conditions a little. I just don't want to go into this mechanical power. This mechanical power is a little bothersome. You see this equation here, we have a sum. We have a sum of two terms, and this sum is equal to now the sum of two other terms. So I don't know what the mechanical power is in this summation, and I don't know what the rate of change of energy is. Now you might be tempted to say that one of them is that mechanical power could be IL di by dt or I squared dIL by dL by dt, and the other is, so it's like, crisscross. One of them matches with the other and the other matches with the other. So it's like a kind of double date. But unfortunately, we can't do this as such. We don't know, right? We don't know which is what, and we don't know if any one term corresponds to any other term as well. We just know that the sum of these terms corresponds to the sum of these two terms. Now, what if I don't have this mechanical power? If I don't have this mechanical power, I am now simplifying my equation a little. In that case, I have only the rate of change of energy to think about. And this would happen if we say that this circuit is now not a motor, but simply an inductor. And that's what I'm trying to do here. I'm assuming that the circuit feeds a simple inductor. Now, the only problem is, if I were to now simplify it to the extent that this inductor is also a constant, then in that case there is really nothing left. It becomes trivial. So we don't want to go that trivial either. So let's say this is an inductance, but it's a variable inductance. Don't worry about how it is variable. It is just variable. Now, if we take this, we now see that this voltage is equal to the differential with respect to time of the product of the inductance and the current. Now, where am I going with this? Supposing I say that multiplied V into I, and I say VI is D into product of L into I divided by dt. Now I'm going to go and correct that auto caps. Alright. Oh, come on. I think you have to press at least once and go. Okay, good. So you see, I am multiplying both sides of the equation by the current. So I have V into I on the left hand side, which is the electrical input power. And I have on the right hand side the product of the current and the differential with respect to time of the product of the inductance and the current. Right? So we are somewhere near here again. So, but we've already achieved this. There's nothing new. What do I need to do? I need to go one step further, and I need to go somewhere here. I need to start talking about energy again. And if I want to talk about energy, it's quite obvious what I have to do. I have to integrate this equation. So if I integrate this equation from, let's say, 0 to t, so I'll just put it at t, right? I'll just say this caps of t or hat with respect to t simply means we are integrating from 0 to t. And I integrate 0 to t of this Vi, and I integrate the right hand side as well from 0 to t. So I just say I t Li by dt. So I am integrating, and of course the end of it will also have a dt. Should not forget. The end will also have a dt. So what I am saying is I am integrating both sides of this power equation with respect to time. So I have on this side the input energy. And this input energy is equal to something. The question then arises, what is this something? And this something is what we got to figure out now. That is, we got to integrate this entire term, right? We got to integrate this term with respect to time from a time limit of 0 to t. Let's assume that we are starting at 0, because technically speaking, we don't really have to start from 0. We can start from minus infinity, but for practical purposes, we can say that at time t is equal to 0, this circuit is at rest, and we switch on the power at 0. So therefore, at time t equal to 0, when we turn on the circuit, the motor starts, and therefore at time t it has reached some state. We want to know what that state is by integrating it with respect to time, and therefore we will get at time t an equation, right? So now this lecture has gotten already pretty long, so I'm going to stop here. But where am I going with this? Where I'm going with this is that now on the right hand side, whatever we get, right? Whatever we get is no longer, there is no mechanical energy here, right? So I'll just write this here. What is here, okay, let me just keep writing, is only the energy stored in the magnetic field. Why? Because here we are not taking into account any of the mechanical aspects of the circuit. For now, we are assuming this circuit is a simple inductor, only that the inductance is variable. There is no mechanical component, so there is no mechanical energy, there is no mechanical power. So therefore, and we have already neglected the resistive drop. And because we are neglecting the resistive drop, we are saying that this entire input energy is stored in the magnetic field. Alright, so the question then arises, if I can expand this equation somehow, if I can integrate this and I can expand it into an expression, I now have an expression for the energy stored in the magnetic field. And if I have that expression, I now can start linking them together, right? Because if I have the expression for the energy stored in the magnetic field, I can differentiate that expression, calculate the rate of change of energy stored in the magnetic field, and then calculate the mechanical power. So I'm getting closer and closer to my goal. My goal is to find out an expression for the mechanical power and therefore for expression for the torque. This is what I'm trying to do. And I'm trying to do all this without going into the construction details of the induction motor like what we did before, right? Because we found out that though it's an interesting experience, it is for theoretical purposes not feasible. If you have complex simulation software, yes, it is possible, but for simple theoretical purposes, we cannot use construction details. We have to use something a little more simple. And that's what we are trying to do, right? So again, it might be a little confusing, but for now, I'm going to stop here. And in the next lecture, let me slowly start recapping what we're trying to do, because it's important that how are these equations all connected? Because remember, writing equations alone doesn't help you to learn anything. It's important to understand the deeper physics behind it, to understand how things actually work from basic principles of physics. That's what's important. So again, thank you so much for listening and see you next week where we will continue with this. Goodbye for now.